Welcome to another wonderful lecture for Psych 462, Experimental Analysis of Behavior. And today we will be talking about drug addiction and taste aversion, two lovely, lovely topics. So let's see if I can figure out how to share my screen. And I think I can. And so let's go on and see what we're sharing. So let's talk a little bit about the biology of classical conditioning, and thus, because of that, also some taste aversion and some kind of what we call biology of addiction. I think that'll be, but it's also a learning of addiction. It's a nice combination of the two. So let's see if we can use this a little bit better and get rid of that and talk about this. So in the 1950s, traditional learning theorists assumed that anything could be learned. And we've talked about this before, but they talked about the equal potentiality model, which explained that the choice, oh, good spelling error too, huh? Let's fix that. The choice of any CSUS response, reinforcer, or punisher was totally arbitrary. And as a result of that, that the animal can learn anything. Any CS can be paired with any US, any response can be governed or controlled by any reinforcer or punisher. Once a reinforcer or punisher, always and for everyone in the organism's class, it will be a reinforcer. And finally, the biology is irrelevant and anything can be learned. And I think that most of you would agree that that is not what we would consider good. So thank God, since the 1950s, or almost what, 70 years ago, 80 years ago, we've changed. So the learning theorists began to contradict this equal potentiality principle as late as the 1950s. And physio people in particular, as we learn more and more about physiology and anatomy of the brain, we realized that not anything could be learned, that there were actually hardwired parts, even in the human brain. Basic learning theorists such as Lashley or Tyron began to theoretically hypothesize that not everything could be learned. So they had good reasons why. And then some actually students of Skinner's, who we'll talk about in a couple of weeks, the Brelands, began to argue that there were examples of kind of biology interfering with learned behavior, even when it was operantly conditioned. And they actually did that with a lot of animals in applied settings. We'll be talking about that again in a couple of weeks. And theorists and researchers like Garcia began to notice that there were behavioral side effects of toxins, that once an organism was exposed to a toxin, it would avoid that toxin or be fearful of the conditions that predicted that toxin. And this didn't make sense from classical conditioning theorists because they hadn't explicitly paired any CS with those toxins, and yet the animal seemed to pick up things that were predictive of it. And so the Garcia effect and Siegel's work on addiction were particularly fatal to the law of equal potentiality. And we'll explain why those were potentially fatal, and in fact were particularly fatal. Now, so we know that conditioning of a CS and US of a highly preferred flavor with shock in a shuttle box certainly gets increased movement on the next trial. So when they taste that flavor, they jump. We also know it's extremely difficult to learn, and this is what Garcia was finding in the laboratory early on. And in addition, if there were food pellets in the box that the rat had already earned but not consumed, the rat would grab those pellets and pocket them or mouth them and move them to safety when the shock was about to come. So when the light came on, and again, remember the light would often stay on for a minute or two before the shock, they would quickly grab all the food in their area and then jump to safety, which is weird because they were doing both eating and running from the shock. But think about what you would do when the fire alarm goes off. Do you grab things that are important to you? Traditionally, so do rats. But that didn't make sense from an equal potentiality point of view. So they didn't understand why these behaviors occurred and why you got great learning when illness was paired with a flavor, but it didn't work when you paired a flavor with shock or pain. Because certainly being sick and being in pain are both aversive events, and yet they weren't conditioning equally to a noxious or to a flavor. So a flavor is not equally conditioned to both noxious pain and a noxious illness. So Garcia decided to make this basically his dissertation, and it took him almost 10 years to actually get this published. He started his work in the early 50s and had a great deal of trouble getting this published because it flew in the face of the equipotentiality principle. And what he found was that if you paired tasty water with nausea, which is an illness, you got great conditioning. If you paired what he called bright, noisy water with shock, you got great conditioning. And what on earth is bright, noisy water? Well, it was when the animal, the rat, put his tongue to the water dipper. Remember, you've got a little water bottle with a little drinking spout on it. When his tongue touched that, it caused the lights to flash and the speaker to kind of backwash. So the lights flashed, and you heard this sound, and then the shock came. So whenever you heard like a shorting of the electricity, shock was about to come. Great conditioning. If you drank a novel flavor, maybe you drank lemon water and then the shock came, right? You drink lemonade and then you felt sick. The animal conditioned very quickly. But if you paired the tasty water with the shock, he got no conditioning. And if you paired bright, noisy water with illness, he got no conditioning. And he did this over and over and over again. And no matter whether he tried rats or mice or any other animal, including goldfish will show this, it will not work. You can pair a taste with nausea. You can pair some kind of outside environmental event with shock, and you get good conditioning. But if you cross the two, you cannot get conditioning. And the problem was explaining why. So what we determined was there was a biological boundary that explained this phenomenon. And you have to look at the type of stimuli that are being used and categorize both the CS and the US as internal or external. And then what's the response? Is it an external or external response? So tasty water goes where? Where do you taste the water at? Outside your body or inside your body? Right, inside your body with your tongue. Where does nausea occur? Does it occur outside your body or inside your body? It occurs inside your body. Where is the bright, noisy water stimulus? Is it inside your body or outside your body? Outside. What about shock? Inside, outside. Where does shock come from? If nausea comes from inside. Where does the shock come from? The pain come from? It comes from outside. Okay? Yes, you perceive it on the inside, but it comes from the outside. Just like you perceive nausea on the inside, but it comes from inside. So we have internal to internal, external to external. But what happens when I cross them? I get internal tasty water to external shock, and the animal has a great difficulty learning that. And if I cross my external bright, noisy water with my internal nausea, the animal has a great difficulty learning that. So it turns out you can't cross internal to external modalities well if you want good learning. The learning has to be compatible with the biological modality in which it occurs. And we found that this is true on just about every single organism that's being tested. We can't say all organisms because we haven't tested all organisms yet, but this is a very, very generalized phenomenon. The important properties of this taste aversion is it occurs in one trial. And I ask you, why should an animal learn about taste aversion, or we also called it poison-based avoidance conditioning? Why should it learn about the poison in one trial? What do we call an animal that eats the poison twice? Four-letter word, starts with D, ends with D. It has an E and an A in the middle. That's right, dead. Okay. Animals that live don't go back and taste a noxious taste a second time, especially if it makes you sick. And again, this is a very general phenomenon. It is dangerous for an animal to taste something twice. It shouldn't, and so it doesn't. Interestingly, taste aversion can tolerate a long delay. And this seems to be because it may take a while for the digestive process to occur. Think of like cows, has to go through a number of stomachs. And in any of those stomachs, the animal might feel the nausea. Well, it takes a while until the digestive process is pretty much complete so that the taste can be paired with the digestive process anywhere along that process. This diversion occurs more readily for novel stimuli than for familiar stimuli. If you frequently eat at McDonald's, but you haven't or you've never eaten before at this Hungarian, Italian, Chinese McDonald's, that McDonald's is going to be weird. I mean, how rare do you get, General Chow's goulash hamburger? Yeah, I'd be a little suspicious of that. And so if that happens, it's a novel food and you eat it and you get sick, you're much more likely to blame it on that novel food than a food that you've been eating over and over again, unless the familiar food tasted off. Because a food that you're familiar with that's never made you sick before is less likely to make you sick, probability wise. And so we see that. We also know that the taste aversion occurs differently for different species. Quail respond to the color of the food, not the texture, the taste, or the smell. Birds don't taste real well, but colored food is predictive of swollen grain. So the swelling of a grain or the color of the grain being off predicts bad grain. Monkeys and little kids, toddlers and preschoolers, don't like weird textures. It also happens somewhat in adulthood. People who don't like calamari or octopus, it's actually squid, but they don't like the texture. It's very, very chewy, very, very fishy. And so people don't like that combination of taste and texture. Rats and humans primarily go by taste and smell. We smell food. Think about it. What do you do first? You smell a food to see if it's okay when you take it out of the refrigerator. And then you either get your roommate to taste it, or if your roommate's not home, you take a little teeny tiny taste. And if it tastes off, you throw it. You get rid of it, because things that taste or smell funny are probably not good. Even if it's something you've eaten before, if it's something that doesn't taste right, you'll spit it out and not eat any more of it. And as social animals, animals can transmit bad things socially. We're not as good at transmitting good things socially, but animals, my husband actually did a study where he had rats who were very social animals, tasted a novel food, and before they tasted a novel food, they saw a dead rat, so dead Bob, had the food smeared all over his face with that novel taste and smell. And they would eat less of it if dead Bob had also appeared to have eaten it than if a live rat was eating it. Your Syrian hamsters from Syria, so your Syrian, your big hamsters, teddy bear hamsters, are asocial. They don't respond to social cues at all about a good or a bad food, because they eat alone and they'll actually kill another animal rather than pay attention to it for important social cues. And so, not surprisingly, they don't. So we see social animals behave differently to food cues than asocial animals or non-social animals. So why was this experiment so important? And again, it was done in 1959. Well, it did explain that bait shy behavior. Animals don't want to eat whatever made them sick. So if you ate something bad, you shouldn't eat it again. And we look for cues or things. Was it time of day? Was it the taste? Was it the smell? What qualities or predictors around that bad whatever I ate might have predicted the bad thing? And this can be really important for things like chemotherapy. Do we want to give a person their favorite food when they're puking their guts out from chemotherapy? And research shows no. You want to make sure that they're over their nausea, because if we pair their favorite food with this pervasive nausea, they'll actually stop eating, that they won't eat the normal food. So in chemotherapy, it's a good time to remind you you don't like liver. Okay? So we have to be careful. But bait-shy behavior could not be explained by the traditional 1930s, 40s, early 50s theories of classical conditioning. They also noticed that not all stimuli could be equally conditioned. Again, internal, external, but even the internal or external stimuli varied in their biological relativeness. Again, like the quail versus the monkeys. And so it matters what kind of predictors are used and what kind of taste aversion stimuli are used. So baseline animals certainly showed strong visual elements to define the location of the poison, but it was not so much the exact place, but the context. So it could be a safe place for other things, but not a safe place for that particular taste. And in fact, we know that olfaction serves a very, very strong role in rats. And olfaction both identifies a place and a taste of food. And if you make the place predictive of a bad taste, then they'll avoid the place. But if that place also predicts good food, it will show less inhibition to that place than it will if that place only means bad things. All right. So this made some better questions about the unconditioned response. Is an unconditioned response required? So what's the unconditioned response for X-rays? There's no obvious behavioral response to the poisoning that occurs in X-rays. Yes, you get nausea and you get other side effects, but that's a very, very delayed reaction, suggesting that the unconditioned response does not have to be immediate. It does not have to occur immediately with the unconditioned stimulus in order for conditioning to occur. And in fact, an unconditioned response can be delayed for hours and hours, potentially even days. And again, it suggests that immediate reinforcement or punishment is not necessarily necessary. And it also suggests that things that you would think would be aversive are not necessarily, like avoidance. You're avoiding an aversive response, but the avoidant behavior or the escape behavior is actually reinforcing. And escape means you got away from the shock. You actually got shocked and got away from it. Avoidance is when you got to avoid it completely. And both of those are reinforcing, even though a negative or aversive response is involved. And this created some really interesting questions about how classically conditioned learning works. So, what exactly is a CS and a CR? This classical conditioning only involve innate unconditioned response behaviors. And the answer is likely not. Okay? Is this really classical conditioning? It's taste aversion, or is it operant conditioning? Because the animal has to pick up the food and eat it. So is it being, is the actual eating response what's punished? Is it classically conditioned? So the question becomes, how do I separate out an innate response from a classically conditioned response from an operantly conditioned response? And again, it kind of depends on which half, or really which third, are you investigating. Is getting what you expected and reacting appropriately classical conditioning? Is reinforcing the behavior of expecting classical conditioning, or is it operant conditioning? Is the behavior of expecting a classically conditioned response an operant response? Well, this makes things kind of confusing. And what we're going to find is that classical conditioning and operant conditioning are really on a continuum. And it's very, very difficult to actually tell you this is purely a classically conditioned response or this is purely an operantly conditioned response. And in fact, almost all real world settings are a combination of the two, or kind of in the middle of that continuum. But then Siegel in 1976 made things even more confusing when he began to show how addiction worked and how you get these step down reflexes biologically to drug injections. And you can actually get the opposite or compensatory response to a drug. So Siegel in 1976 demonstrated addiction, tolerance, and withdrawal. And basically he showed that the cues to learning are everywhere in their side the body, they're inside the brain, they're outside, they are everywhere. So the animal's biology, as well as classical conditioning, are going to impact how an organism responds to an addictive substance. So we have to go back into the 1970s and remember how to define addiction. And I'm afraid that this definition really hasn't changed all that much. But the DSM-2 going into the DSM-3, and again, we're on the DSM-5, I believe revised, is what we're the current model for psychological disorders. Here we're talking in the 1970s, DSM-2. In fact, to the side, the DSM-2 still believed that homosexuality was a psychological disorder, did not really bring out autism as a separate disorder. And it believed that addiction was a psychological, not a behavioral process. And so it said it was almost defined as a weakness in a way. But it did better define tolerance and addiction. So tolerance is the decreasing effectiveness of a drug so that you require increasing amounts of the drug to get the same effect. And you become dependent upon the drug. And dependency is characterized by withdrawal. And withdrawal is where you have physiological symptoms that occur when you withdraw the drug. And again, this is dependence. How do we define dependence? As withdrawal. Withdrawal is physiological symptoms that occur only with the withdrawal of the drug, not with the addition of the drug or in the absence of the drug. And typically withdrawal occurs after some prolonged taking of the drug or giving of the drug. Same thing with tolerance. Tolerance takes time, as does withdrawal. So now the question is, do animals show addiction? Well, indeed, most animals will not begin drugs on their own. You actually have to preload them, so you have to inject them with it or shove it down their throat for alcohol. And then once they become addicted to it, so they become dependent upon it, then they will now respond to gain access to the drug. So your initial responses to drugs such as morphine, the morphine causes decreased responding because the animals are feeling better. They feel no pain, they're stoned, they can't press, but as the drug wears off, they will then respond to gain access. And animals do show tolerance with withdrawal. So once they're addicted, it's the same process over time, and the symptoms can indeed overlap. And this was given as evidence that the process must actually be physiological in nature, not psychological. We wouldn't say the animal was weak because it became addicted to morphine. We did it to them. So we can, and all rats show it. So it has to be a physiological process, not a psychological process. And hence the tide began to turn, although it still has not completely turned in society. Opiate tolerance is defined really by the associative characteristics of the drug administration. It's administrative procedure, sure I could talk. It shows that it's the associative pairing of the drug with some kind of injection process. So how did the animal get the drug? Was it injected? Then that injection becomes associated with the drug. And this is where we begin to see tolerance maintained over long periods of time, even though it's a physiological effect. And this occurs even after what we call ECS, or we can do this electroconvulsive shock. Basically, they use that as a memory disruptor. They did a Control-Alt-Delete of the brain. And interestingly, the tolerance and the withdrawal symptoms remained in the brain even after you reset the brain. It seemed that it was a long-term memory issue, not a short-term memory issue, and was not wiped out by things that wiped out short-term memory. And opiate tolerance shows several characteristics. Again, the retention of tolerance is long and strong. Metabolic interventions change the parameters of the tolerance, and retardation or slow list of consolidation of tolerance occurs when you add memory disruptors. So frequent memory disruptors will certainly slow the consolidation of tolerance learning, but it won't eliminate the consolidation of tolerance learning, which is curious. So how does this occur in classical conditioning? Well, drug tolerance, again, is a decrease in effectiveness of a drug with repeated usage. So what? And Siegel proposed it's completely due to classical conditioning. And he demonstrated this using morphine, an analgesic, or what's called an opiate agonist. It mimics the effects of our opiate receptors, which release natural endorphins. So with successive morphine injections, an animal appears to show a decrease in analgesia, which are controlled by contextual stimuli. Let's say that in English. He did his original study with rats, and yes, a hot plate. Yes, like a plate that's hot. The things you use if you don't have a stove. So rats were given injections of morphine across several stimulus conditions. The first 3 trials, he kept the cues identical. So the animal was given an injection of morphine. So there's a shot, like a syringe, morphine, And how did he test how much analgesia the animal had, how much pain relief the animal had? He looked to see how long the tail could sit on the hot plate before it would flick off, the tail flick test. So the more analgesia the animal had, the longer it would allow that tail to lie there. It didn't respond as much to the hotness of the plate. So first 3 trials, they kept everything the same. But on the 4th trial, he changed the location of the injections to the home cage rather than the experimental room. So the first 3 trials, the experimental room. 4th, they got their injection in their home cage and then were transported to the hot plate test. And he got an increase in analgesic effects. So here, the animals were, on the first 3 trials, they left their tail shorter and shorter times because the morphine was less and less effective. And on the 4th trial, it was as effective as the first time. And the question was, why did these context cues, this change in location, acquire the capacity to elicit compensatory responses of hyperanalgesia? Yet when the context changed, the cues were gone. So why did we show this tolerance here, but no tolerance on the 4th trial? And so Siegel had to come up with an explanation for this. And I hate to tell you this, but he wouldn't have done the experiment if he didn't have a hypothesis as to why. So he argued it is difficult to predict the form of the conditioned response. It could be identical or very similar. It may be opposite. And it has to do with the compensatory responses that compensate for or counteract the unconditioned response. And there was a variety of literature that supported this at a time. Go to that slide in a second. There we go. So if we had epinephrine, the response to epinephrine is tachycardia. So you get a huge increase in heart rate, and the opposite response is brachycardia. Epinephrine, you get gastric secretion, but you also get gastric secretion as a response. Epinephrine, you get hyperglycemia, but hypoglycemia. Epinephrine still maintains gastric secretion in both situations. So your unconditioned response and your conditioned response, but it shows opposites for your glycemia. Glucose, you get an increase in your blood sugar with injections of glucose. Well, yeah, you're injecting sugar, and you get your hypoglycemia as a conditioned response. Insulin is the opposite. Nicotine, you get hypoglycemia, release of sugars. You get hypoglycemia as a conditioned response. Atropine, you get this anti-salivation or anti-lack of salivation, basically lack of salivation, hypersalivation, and so on down the thing. And so some drugs produce similar responses, some drugs produce opposite responses, and you almost have to test them to figure out what's going to happen. So why would this occur? Well, he goes back to the good old opponent process of Solomon from the 1950s, actually 40s and then into 50s, Solomon and Corbett. And again, we have the A response and no B response. And in the A response, but no B response, we just get A. So this is how much we're going to get. If we get a B response starting to come up after our A response, so here's our A response, here's our B response. We add these two together, and that's the size of the response. Our C response, this time, here we go. So what he's saying is that we learn that for every reaction, there is a reaction. Can we predict the response? Figure A, there's no association yet, so we just get A. The drug is not yet associated with the pre-drug environmental cues, so the drug effect is not yet modulated by any anticipatory responding. But in figure B here, as the effect of the drug increases and decays following administration, we get increasing frequency of the drug environmental context pairings, right? Because each time we do it, we're getting a drug environmental context pairing, so we're getting more of this compensatory response, and this takes away from the A response. So drug administration is not only followed by the pharmacological unconditioned response, but also by the drug compensatory response. And the net effect is a smaller than initial compensatory response because the drug UR is attenuated, reduced by the compensatory response, right? Let me say that again. The net drug effect you get a smaller than initial CR because the UR is attenuated by that compensatory response. And in C, the interaction between the drug UR and the preparatory CR after many of our trials is that the CR is large. The net result of the interaction between the CR and the direct drug effect is very small. But notice there is some biphasic or paradoxic conditioning or opposite conditioning effect. And you can actually become hypersensitive to effects at higher doses. And that's how you die. We'll talk about that in withdrawal symptoms in a minute. If I get hypersensitive to it at a higher dose, I actually think something's going to happen when it actually doesn't. And my body compensates more than it should. And I can actually die as a result of that. So what are the learning effects? Well, I get physical effects. My body is rebounding the opposite way when I expect something. And if I expect something, but it doesn't happen, then I get a different kind of effect. And what's actually happening is we're getting something called step-down reflexes. The alpha and beta receptors on the opiate receptor are altering how the opium or the morphine is actually processed by the cell. And if I do this enough, at some point, my step-down reflex can't occur. I've pretty much blown out that cell. Well, if I'm not getting the compensatory response and I put in drugs, so say my initial drug is 10. I do 10 units of morphine. On trial 2, my body says, aha, I know you're going to give 10, so I'm going to step down by 10. Well, now you get nothing. 10 minus 10 is 10, right? So now you go, I'm going to go plus 20. And on that trial, plus 20 minus 10. Oh, now your body says, wait a minute, I got an effect again. So your body on the next trial does minus 20. Plus 20 minus 20, it's a walk to 0. And so on and so forth. But if your body stops the step down reflex, and you do a massive amount of dose expecting the step down reflex, guess what? You just overdosed. And you overdosed because your body didn't compensate when you were expecting it, and you added more drug to offset the compensatory response. And notice in this, the needle begins to be the predictor or the CS for the heroin. But you also get an opposite effect to process B to the needle. Oh, the needle means the drug is coming. I better do that step down reflex. And so the stimuli can become conditioned to the emotion of that needle coming. The actual kind of excitement towards the drug causes me to step down and not want or to reduce my reaction to the actual drug. So what stimuli serve as cues? Well, any stimuli cue predicting the drug. And tolerance occurs because of the context of the environmental cues that predict the drug. And in a sense, tolerance is a learning effect. It's not a drug effect. Tolerance is a learning effect to environmental cues. And those cues that are environmental are cues including outside the environment, physical effects, and what we would consider psychological effects as well. The environmental cues can be the place setting, the room, the lighting, the people you do it with, the experimenter, the time of day, but also olfactory cues, how you're feeling, the state of your body, and the initial effects of the drug. So these cues become extremely complex and difficult to predict, both by an experimenter and by the addict doing their drugs. So again, what stimuli serve as cues? Both signaled and unsignaled. Signaled cues would be the syringe is a definite signal, but time of day might be an inadvertent signal. Your friends might be an inadvertent signal. The room might be an inadvertent signal. You didn't mean for that to become a predictor, but it becomes a predictor. And this can develop discriminative control of tolerance. You show the step down reflex in some settings and not others, and it depends on the similarity of the cues to predict the degree to which you'll get a step down reflex. So if the room is similar, you'll get a similar predictive cue, but if it's very different, you won't. And that shows why you get different responses. So it's not even so much the change of the quality of the heroin you might be doing, although that could certainly have an effect. Certainly doing it in different contexts can change your response to the same heroin. Complicated, isn't it? We can also get C habituation. You get partial reinforcement of tolerance. So you get some different street drugs. So you get street drug A and street drug B, but you always do it in the same room. That can cause some partial reinforcement of the tolerance. Your tolerance builds up, so to speak. It becomes stronger and bolder. So not all CSs are followed by the same US all the time. You get this diluted CS-US relationship, which makes it more difficult to extinguish because it's richer. It's not 100% predictive. It doesn't have to be. It just has to be predictive most of the time. And those many cues then are allowed to condition, where if you had one very strong, think about your overshadowing and your blocking. Here we've got almost the opposite effect. You don't have a blocking stimulus. You have hundreds of teeny tiny cues, and none of which particularly overshadow one another. Well, then any combination of those cues can elicit tolerance and withdrawal. So expectancy effects. I expect to get stoned. And expectancy effects can be very, very strong. I had a friend who did a study looking at the effects of alcohol on your focusing response. They were looking at pilots and how it changed focus on the eyes. And they actually found that something like 0.01 alcohol levels caused significant changes in the ability to focus. But they had some placebo conditions, of course, when the people were told they were given alcohol, when really all they got was tomato juice and a piece of celery. And interestingly, they had a couple of people who acted very, very drunk, even though they got nothing besides tomato juice. And that's an expectancy effect. You think you got the drug, and because you expect it, you actually get the compensatory response and then the actual response to the drug. And so you can get these expectancy effects, and they're simply withdrawal effects are occurring because you expected the drug to happen and the drug didn't happen. And so you don't get quite the result you expected. I thought I was going to get the drug. My body stepped down. It anticipated the drug. I got nothing. So if you think of it with morphine, I hurt more as an expectant effect of thinking I'm going to hurt less. Well, if I got nothing, I hurt more, right? If I'm going to hurt plus 10 and as an expectation of hurting minus 10, well, those wash out for my step down reflex and I hurt 0. But if I increase my expectancy of plus 10 and I don't get any drug, now I hurt plus 10. And that's what's happening with withdrawal effects, is because you didn't get the drug, but you still had a compensatory response, you hurt more. Your effects are worse. This could actually happen with nose drops. You stop taking your nose drops if you use it for too long, say for more than 7 to 10 days. You actually will, at the site of the nose drop bottle, start to have a stuffy nose in anticipation of the nose drops helping you make your nose stop dripping. Weird, huh? But if you don't take the drug, then your nose just is stuffy all the time. So you have to be careful not becoming addicted to nose drops as well. So what component effects can we get? Well, to opiate administration, you get hypothermia. Opiate withdrawal, you get hyperthemia. The morphine makes you cold, so you feel hot during withdrawal. You get decreases in blood pressure, you get increases in blood pressure with withdrawal. You get peripheral vasodilation, your skin feels flushed and warm with opiate administration. You feel cold, chilliness, piloerection with your flesh, even though you feel hot. All these effects are basically just the opposite. Obviously, you're euphoric, you have less pain, and you feel relaxed in opium. You are restless with insomnia, you're irritable, and you're depressed when you don't get your opiate drug. Sound like withdrawal effects? Yeah. And these are really important when dealing with addicts. These are the symptoms they're going to feel the moment they stop taking their drug. And of course, taking their drug is going to relieve these symptoms, which simply reinforces drug taking. And again, we get some hierarchy of stimuli. And this is from a table looking at alcoholics. And one of the top things that people report is being offered just a taste of a drug by an old buddy makes you feel like you want to shoot up. Seeing a friend shoot up a drink, talking about drugs on a corner, standing on a cupping corner as your drug corner, seeing a successful pusher. But importantly, awkward social situations, job interviews, family criticisms, feeling like an outsider, talking about drugs and group therapy, seeing heroin, seeing pictures of heroin, seeing pictures of an anti-drug poster where somebody is shooting up with a big X across it. Well, even though it's got an X across it, that may be a predictor of a cue to take the drugs. And it may actually, anti-drug posters may actually elicit drug taking from addicts. Is that not weird? Yeah. We learn predictors and then we crave the drug. We get those withdrawal symptoms because we want the drug to take away those cravings. Now, some of this had to do in the brain with your step down reflex and autoreceptors. And the neurons have special regulatory receptors that line the synapse. So they're in the end of one synapse, and then the synapse. So the end of one neuron, there's a space called the synapse, and then the beginning of the next neuron. You know that. And on the end of that first neuron, there are some autoreceptors that line it. And these autoreceptors sense how much of a neurotransmitter is released, how much neurotransmitter is remained in the synapse after an action potential, and how much is reuptaken by the cell. The idea being that they're going to auto-regulate the production of neurotransmitter. So by knowing how much is out there, it knows how much more to produce. Because if you emptied your sack and it contained 100, then you need to make 100 more, unless it didn't all empty or you got to take some back up. So when you flood the synapse with the agonist, with the morphine, it basically alters the ability of the autoreceptors to do their job. The readings from the synapse are now in error. And the result is that the cell either overproduces or underproduces the neurotransmitter that will be released after the drug exposure, and the drug begins to hijack the system. And so now that drug is artificially telling the neuron how much to take to produce. So if you're taking, say, 1,000 morphine units and your body normally produces 10 opiates to a certain situation. So I get a paycheck, I get 100 opiate units released. I get a kiss from my spouse, that elicits 150 opiate units, but my morphine gives me 1,000. I now base what I need on that 1,000 of the drug, and the 150 or 100 units produced by normal reinforcers no longer is sufficient for me to feel sated, so to speak. It's no longer enough to please my little neurons, and I will still crave the drug, and I'll crave this new 1,000. So the autoreceptors literally are reading too much. And the result is often a decrease in the neurotransmitter release. So the body is in a deficit state post-drug. And so the drug will be compensating. The neuron either have to keep producing more or you'll have to take more drug. Well, you can't produce that much that the drug gives you naturally. And so how do you get that much? You get it through the drug. And then at some point, your autoreceptor shut down. You've blown out that neuron, and now you're completely dependent upon the drugs to have any kind of opiate or endorphins at all. And so now there's no feedback system, and you're completely dependent on the drug. Worse yet, there are strong data that suggest that even with relatively short addiction, the autoreceptors may be permanently altered, and you with this long-term drug exposure, the longer you take the drugs, the more permanently they're shut down, and now you cannot either regulate drugs or your normal neurotransmitter regulation. And the question, really the million-dollar question, is going to be whether or not you can fix this. So the drug is the release of the dopamine. So if you as a drug, you are of drug effects. Stimulus predicts that the drug predicts the drug that releases a DA. So the CS of the Q is this US of the drug predicting the UR of the drug effects. So your anticipation of reward is the dopamine release. But your body prefers homeostasis. No sudden changes, maintain the level. So when you have the Q of the CS predicting the US of the drug, which predicts the UR of the drug effects, the CR is a decrease in dopamine release in anticipation of the drug dopamine release. And the body reduces dopamine in anticipation of an increase in dopamine or morphine. It could be an increase if the drug is going the other way. But basically, this Q is altering the normal response to the drug and is typically doing it in the opposite direction of the drug effect. And if you overdo this system, you no longer can regulate it. Naturally, you're completely dependent upon the drug. So as the body reduces dopamine in anticipation of a dopamine drug, such as now we're talking cocaine, you no longer get the same effect for the drug and you have to take more and you get tolerance. You stop taking the drug, no step down reflex or compensation. So now the reduction in dopamine in anticipation occurs, but no dopamine comes. So now you have too little dopamine, you get shaky, motor tremors, etc., and you get withdrawal. And the setting cues predict this reduction in dopamine, even in the absence of you taking the dopamine drug like cocaine. And so setting cues are important. Just change the direction of this for morphine. But the step down reflex is exactly the same. It's altering or hijacking your system. And if you stop taking the drug, the cues predict your compensatory response, but no drug comes. And so you get the icky compensatory responses. And you have to take more drug to get rid of those withdrawal effects. And then you become even more dependent until you're dead. And withdrawal or addiction will eventually kill you. There's no doubt about it. Addiction is a fatal disease. If you keep using, you will die. You will die. But interestingly, who becomes addicted may be an individual effect and not the addiction itself. It appears that people who are likely to get addicted tend to show lower levels of D2 autoreceptors. In fact, most addicts show lower levels of these D2 autoreceptors, the autoreceptors I talked about on the neuron. And that those with a high number of autoreceptors find drugs unpleasurable. So they don't like the effects of the drugs like opiates or cocaine, and they're far less likely to use the drug, but those with fewer report greater pleasure. And we know that these D2 autoreceptors help regulate dopamine tone as well as your endogenous opiate tone, and they regulate reuptake and production of both. So it appears that dopamine drug addicts, as well as your opiate drug addicts, because that actually affects dopamine, have a reward deficiency syndrome. People who are likely to become addicted to dopaminergic or your endogenous opiate drugs may have insufficient receptors to respond to DA and need more dopamine to get the same effect as people with normal levels of dopamine. So they are actually in a constant reward deficiency craving state. And when they do take a drug that resolves the state, it has a more powerful effect. So who's that? Well, again, we know that addicts have this. In fact, they show a permanently changed level of these D2 autoreceptors. And they've taught the system to detect only very large changes in neurotransmitter. So normal cues and normal neurotransmitter release are no longer enough. We've said that. Paychecks, spouses, children's, jobs, nope, no longer are enough release of dopamine or endorphins to produce normal reward responses. Only the drugs do. But the question is, can we unteach the neurons and return them to responding to typical changes in dopamine or endorphins? And can we take people with too few D2 autoreceptors and somehow maybe through mental exercise or maybe engaging in typically pleasurable events, increase their level of D2 autoreceptors to a normal level? We don't know. And that's the honest answer right now. It looks like we may be able to unteach early on in addiction, but we never return the body to a normal level. And people who may have these genetically altered levels of D2 autoreceptors may never gain the typical level, and they may have to actually be very careful and, in a sense, learn to respond to lower pleasurable levels of reward. PET scans can actually show this. Here's a cocaine abuser, and here are neutral cues. So here's a neutral cue and the response in their various little areas of the brain here. So the prefrontal area, and they respond more here and here, but here are they responding to the cocaine. Look at this. Again, red is more activity. They get more activity here. They get more temporal lobe reactivity, or some of our prefrontal and nucleus accumbens dopamine pathway is going to go through the temporal lobe. So it goes from here to here to here. And we see much more activity in a cocaine abuser as opposed to a typical person. So even in the neutral cues, here's neutral cues, here's a normal person, a cocaine abuser. Not cool, is it? Yeah, cocaine cues, neutral cues, cocaine cues. Neutral cues, cocaine cues to a typical person, to, yeah, not good. So what's the bottom line? Addiction is learning, and learning produces changes in the brain. Addiction is learning because it produces the very same changes in the brain that occur with learning, particularly step-down reflexes and neural compensation. And neural compensation results in behavioral compensation as well. Step-down reflexes in the brain result in behavioral changes in our learning. We respond differently to predictive cues because of our step-down reflex. We wipe out the step-down reflex, we get overdoses. We change our cues that predict the step-down reflex, we get overdoses. We get greater or less withdrawal depending upon the cues that predict the drug. And so we get significant changes in the situation that are indeed learned. So how do we treat addiction? Well, we can use agonist treatments. We can replace an addict with another drug. And so we often use a drug, a synthetic opiate called methadone, that is less addicting and has less of the deleterious effects. So it doesn't have as many side effects, and we just put the person on methadone permanently. But what do the data show? Well, if we can get them to stay on methadone, it works. But methadone is not as powerful a pleasurable drug as your opiates. And so they'll switch back to regular opiates because they get more bang for their buck. And every time they switch back and forth, they train the brain to like the opiates better than the methadone. We can give an antagonist treatment. So we can give drugs that block the effects of the addictive drugs. And that's what Narcan does. Narcan is an opiate blocker. So the opiate drug has no effect. And so when I injected that into you, it immediately stops the effect of the opiate you just took. And your body then is fine. It wakes up. And we can put you on low levels of Narcan. The problem is treatment compliance. People won't stay on the Narcan. Absolutely will not stay on it because they're not getting the reinforcer effects. And a big problem with the Narcan is not only do you not get the reinforcement effects of your opiate drugs, you also don't get the reinforcement effects of normal behavior. We can give you drugs like antabuse for alcohol. Antabuse makes you puke when you have any kind of alcohol in your system. And this can be a problem if you get some like vanilla extract, which is actually alcohol based, in a very small amount of alcohol. A mouthwash, it can induce you to puking. Well, puking for days on end is no fun if you drink, so people won't stay on it. Another experimental strategy is actually to interfere with the dopamine reward system itself. So not worrying about the drug you're abusing as a dopamine drug or an opiate drug, just to bypass that. And baclofen, which is an experimental drug, reduces dopamine activity in the ventral tegmental area, which is one of those primary brain reward areas, and by activating GABA. GABA is the GABA reduces the ability of dopamine to work. And so it stops the action of dopaminergic neurons. But by doing that, we also increase GABA in other areas of the brain. And GABA release is basically what Valium does. You get very relaxed muscles, but that causes problems in digestion and thinking and a bunch of other areas. And the problem is you've got a closed system. And anytime you make a change in one thing, you're going to cause a chain in the other. And if you think about it, it's the old idea that a butterfly flapping its wings in Africa causes a snowstorm in central Illinois. Yeah, you've got a closed weather system. And so any kind of change in the weather system causes a change somewhere else. And that is very true in the brain. We don't know a good way of stopping this addictive process because this process is important to have. It's also negative to have. We need this addiction system to learn what rewards are, but we don't want it to learn what drugs are. And so we have to be very careful with what we're learning about reward, I guess is the important part. Aversion treatments. Again, and abuse. We can give people other drugs to make you stop overeating or start liking things. But again, it interferes with the system. They're now trying some anti-drug vaccines that are actually synthetic molecules that resemble the drug, but they've been modified to stimulate the animal's immune system. And that makes the antibodies degrade the drug rather than the dopamine itself. Because the drug, of course, is not an exact mimic of dopamine or of the endogenous opiate. That has some promise, although again, we worry about generalization in our learning system because we know our learning system is so robust. We know our immune system learns to respond to a variety of stimuli, and the immune system can be conditioned the same way. And so can we condition it so that the immune system will then begin to attack endogenous opiates or endogenous dopamine, which could be very deleterious and even fatal. So if genetics plays a role in addiction, who inherits it? Well, most of the research again suggests that it is a syndrome of related dysfunctions. And addicts seem to have family members who also have schizophrenia, bipolar disorder, depression, ADHD, and related disorders, autism and autism spectrum disorders. And basically, the genetic propensity for addiction seems to be almost a dopaminergic dysfunction. There are several alleles or alternative forms of a gene that are responsible for development of the D2 subtype of the dopamine receptor. And all those various alleles are associated with these different kinds of psychological disorders. We don't know enough about those psychological disorders and how they're related to these various alleles to definitely alter for gene therapy to kind of prevent you from becoming a schizophrenic or have autism or not be an addict. We don't know enough. It would be very dangerous at this point to do any kind of that drug treatment. But again, it suggests that there may be a genetic, and at least we know there's a strongly familial presence of addiction in families. If you have a family member who is an addict, you are much more likely to become an addict yourself. And in fact, many people who have addiction in their family refuse to drink or most don't engage in drugs of abuse, but to take even opiates at the hospital or try to take the less addictive versions in order to avoid having that opportunity for their brain to learn about addiction. Now, we do know there's some real strong effects, and it's a real world interesting effects. And you read in Siegel's 2016 article about the Vietnam drug addicts. And the question is, why didn't the addicts who were taking amounts of heroin that could have killed a horse and didn't in Vietnam? Well, you had stress effects helping against the effects. You had such a huge stress effect that it took a whopping amount of heroin to knock down that stress effect and give them the pain relief and the pleasure effects that they were wanting. But that didn't happen. They didn't crave or want the opiates when they got home. Well, typically, we're not fighting any kind of guerrilla warfare in the jungle at home. And it turns out that those cues were so very different between Vietnam and home that we didn't see, in a sense, that generalization occur for the learning. We know that animals, even in the laboratory, show strong relapse to various drugs, which is interesting because, again, it suggests that all we have to do is, even though we're in a different experiment, if the experimental cues are the same, so we use a light, We can muck with that animal's physiology and it can crave a drug from a previous experiment. We know the power of inadvertent cues. Just ask any addict. Somebody who's tried to quit smoking or you've tried to quit caffeine, any kind of little cue can be extremely powerful and re-elicit those cravings that occur with withdrawal and therefore the cravings of using. And the bottom line is conditioning occurs everywhere, and addiction is just a very, very powerful form of classical conditioning, probably with some operant conditioning thrown in. So, what does this mean for applied settings? Be careful to environmental cues. Remember that learning is robust. Remember that there's a strong genetic component. There may be a predisposition, but not an actual addiction genetically. And so my question to you for Thursday is, how do we design detox and treatment centers? And how do we help people learn what the behaviors they learned in detox and treatment and generalize those to the real world? And what happens when we put individuals back into their original settings? How can that affect what we do? And so we'll see if we can get ourselves back to our original situation by stopping our share without the cat helping me. And as you can see, I've sunken now. Perkins has joined us, but we do have a helper over here. There he is. He keeps helping me by jumping on my keyboard and moving me around as I've been doing this. So I will sit up a little bit, put my camera back down after he's batted it, and we will see you all on Thursday. Take care.